Swayam Prabha. Digital India. Educated India.
Yeah, so it says that should be matched in M. Moreover, so M of P belongs to every F post P is matching. M of P belongs to F of P. What this statement says is that the matched partner of P is coming from one of the applicants who treat it as its rank 1 and nobody else, right? So without knowing whether a popular matching exists, what we are saying is if a popular matching exists, it must look like this. So if in this previous instance, if somebody gives you a matching in which A2 is matched to, so there is nobody who is, so let me add something. So maybe I'll just add here P3, P2, P4, P1. So if there is a matching in which, if somebody gives you a matching in which A4 P1 is matched, then you should immediately say that such a matching cannot be popular and discard that matching from being under consideration for being a popular matching. Is this clear? Okay. So we still have some more work to do to say how does a popular matching completely look like. So this is the first claim. So now if you look at the preference list, so this is an abstract instance A1 to AN, and there are these F posts, some P1, P2. I don't know whether the F posts are unique and so on, but there are some F posts. So what we are saying is that these F posts have to be matched, and they have to be matched to somebody who treats it as a rank 1. We do not know whom to assign them to, but you can think of them as being matched to somebody, right? So if there are some remaining posts, I mean if there are not enough posts to be matched amongst the F posts, there are some applicants who need some other posts, right? Then everybody need not get matched to their first post in a popular matching, but there may be some other posts may be of use. But if there are some other posts, there must be other posts which are left over after F posts have been removed. So what we can think of is take the instance and remove the F posts from everybody's preference list. That is, even if a post, so let's say P1 is an F post, P1 appears as a third choice in A3's preference list, it doesn't play any role because this A3 P1 edge is never going to get used in any popular matching. This is what the theorem states. So therefore it says that you can think of the graph being reduced. That is, you of course are interested in using these first choice edges, and we have not fixed the matching, but you are free to delete these edges. That is, A3 P1 is no longer playing any role. It can as well be discarded. So we can think of a reduced instance. Good. So yeah, so I don't think you should keep copying the instances because I do keep changing, I'm sorry. Okay. So Okay, so if this is my instance, I know that I should add these edges A1, P1, A2, P2, A3, P2, A4, P2, A5, P3, right? These are interesting edges. I do not know which amongst this is going to get matched, but these are interesting edges. Similarly, there are some edges which are uninteresting or irrelevant for me. And what are those edges? For example, this edge, A1, P2. So I will just say that this is a discarded edge, A1, P2, because this post is a rank 1 post and I am never going to match it to somebody who doesn't treat as a rank 1. Similarly, A2, P3 is a discarded edge. A4, P1 is a discarded edge. And A5, P2 is a discarded edge, right? So now I have some reduced instance. F posts are anyway, I have added those edges to their rank 1. I have also discarded some edges based on the fact that these edges are never going to get used. That I have proved, so I have not done something wrong. So now where should I look for some remaining edges to be added? So because as you can see, A1 gets happily its first choice, but A2, A3, A4 do not have posts to be added, I mean do not have enough to be matched. So they need some more posts. Yeah, so what edges should I add for applicants? Okay, A1, P3, okay, thank you, yeah. Yeah, so that is also a discarded edge, yeah, good. Yeah, and anyway in this example A1 doesn't need anything, but yeah, that's correct, I am never going to use that edge. But what do you think after the instance has been processed to some extent? Where should I, for example, A2 needs something more. Does it have anything? No. The only edge which was A2, P3, we cannot use it. What about A3? A3 does have P4, right? So it is possible. Let me just add one more P5 here. A3 has P4 as well as P5. Which do you think it should add an edge to? Again, it seems intuitive that it should add an edge to P4 rather than P5. When there is something better available, we add it to that. So again, we will try to add that and see whether we can formalize this. So let me add this edge A3, P4 and A4, P5, right? So what I will call this is that, so what I have done is for every applicant I have selected its F post and added edges to that. That was my first step. Then based on whatever are F posts which are appearing in the preference list of some applicants as non-F posts, like P2 was appearing in A1's preference list as a non-F post, I deleted that edge or discarded that preference. And now amongst the remaining posts, whatever remains, I am asking what is the most preferred post that you have, right? So the most preferred post that you have, I am asking and I am adding that as my second choice, the next choice. So I am constructing a graph which is a very small graph as compared to the original graph. The original graph has many edges. I am constructing a graph in which every applicant has at most 2 edges. One coming from its F post, the second coming from another post which if it is available, because for example A1 there was nothing else to add, A2 there was nothing else to add. So we will call this as the S post. It is called a second post of an applicant, and the S post of an applicant need not be its rank 2 post, but it is the most preferred post which is a post which is a non-F post in its preference list. For example, I will just add P3 here to make this look different. So if there was P3, then this edge is a discarded edge. So the rank of P4 in A3's preference list is indeed 3, but it is called its S post. So an S post of an applicant is the most preferred non-F post in its list. So I hope it is clear what it means non-F post. So F posts are posts which are called as are rank 1 post for any applicant, and we have done a pre-processing of the preference list. That is, we have deleted all the edges, or deleted or think of marking edges, marking posts which are F posts for somebody. Of course, you are not going to mark, you are not going to delete something which is your own F post, because that is your F post. But if any post which is ranked as an F post which appears in your preference list at other rank, you delete it, right? You think of that edge being deleted, and then whatever remains, you will call it as your S post. Whatever is the most preferred post, you will call it as an S post. Is this definition clear? Yeah. So we have just listed out, so list out all the F posts. So in this example, P1, P2 and P3 are F posts. Is this clear? So go to every applicant's list. Of course, do not touch its F post, and then ask, is P1 appearing in your preference list as a rank 2, rank 3, anything? Wherever it appears, just delete it. Delete or think of it as being marked as not available for you. Right? Remember that if P1 is your F post, it cannot be your rank 3 or rank 2 and so on. So your own F post will not appear at a lower rank, but somebody else's F post can appear at a lower rank. Is this clear? Okay. Any other question about? Okay, so will an S post always exist? No, right? This example itself shows. For example, A1 doesn't have an S post. A2 doesn't have an S post. A3 does have. A4 has an S post. A5 doesn't have, right? So we would like this S post to exist, right? We would like this to exist. So what we are going to do is, we are going to do a small pre-processing of the instance. That is, as soon as we are presented with the instance, we will say that I will add a unique last resort post for every applicant. So LA1, LA2, LA3, LA4, LA5. These are all dummy posts, right? Think of them as just being there as placeholders. So we will see that their addition is not going to change the answer to the question, does this instance admit a popular matching or not? It will not change the answer to this question. Whether they were present or they were not present, the answer will remain the same. But it will make some of the things easier for us. So what have we done? We have added a unique last resort post for every applicant. That is a dummy post. Think of it as a dummy post. Now when I scan this list, when I am deleting these F posts or unnecessary edges, this post will never get deleted, right? Because this is not an F post for anybody, so this will be untouched. So if nothing is there in your preferences which is a true post for you, then your dummy last resort post certainly qualifies to be an S post, because that is the post which is the most preferred post, which is a non-F post. So therefore now S post always exists from now on. So F post certainly is there for every applicant, because we know that preferences better be at least having one post, otherwise the applicant doesn't want to participate. So therefore F posts exist. Now by this pre-processing, S posts also exists, right? Okay, good. So now so S post may not come into picture always, because as we see A3, doesn't even care about its last resort post. The last resort post need not come into picture. For example, A3's S post is its true post, which is P4. A4's S post is P5, but A5's S post is L of A5, right? So now S posts exist, and for some applicants they may be the last resorts, for some applicants they may be true posts that were there in their preferences, right? Okay, good. So now what people observed, and this is a very nice result, and the whole thing that I am presenting is from a paper in 2005 by several authors, which include Abraham et al. And we will share the paper as well as the paper with you so that you can read it. So they observed a very nice thing, that is, now you construct this graph where every applicant has only two types of edges. One, its F post edges, which we have already drawn, and its S post edges. That is, every applicant adds an edge to its S post. So let's do that. So here we have added, but we have some more edges to add. That is, A1 can get assigned to L of A1. A2 also has L of A2. A3 already has P4, A4 already has P5, A5 has L of A5. Right? So this is what we have. Now this is a graph, very simple graph. It has, every applicant has two edges, so the graph has 2n edges, right? It has exactly 2n edges. And now if this graph admits a matching in which every applicant is matched, if every applicant has a post to be assigned to, then that matching is going to be popular, right? That is, if you can find a matching in which you can get a post for every applicant in this graph, in this reduced graph, then that matching is going to be popular, right? So this is what we will like to show. But before we show this, let's see whether we understand this. So now in this graph, do we have a matching which matches everybody to either its F post or to its S post? Because that is what the edges we have drawn. So is there a matching that we can find? So a matching is just again a collection of edges, yeah. So can we find a matching in which every applicant gets matched? Yeah. Do you have some suggestion? Yeah, so I don't know your name. Second row behind you. Yeah, behind you. Yeah. A1, P1. LA2, okay. A3 to P2. P5. A5 to P3. So very nicely what you have chosen is that whenever there was a choice between a true post and a last resort, you very nicely chose the true post. Did you do this consciously or it happened? Did conscious? Okay. Okay, but if that was your intent, maybe you could have also done A3 to P4 and A2 to P2, right? So if that was your intent, you could have matched A3 to P4 and A2 to P2, right? That would have avoided even the LA2, right? But what is good about this is that even when the algorithm had or even when her matching algorithm in her mind had a choice to match A1 to L of A1 versus P1, she did choose A1 P1, and that must be chosen because we know that every F post must be matched. If one chooses a matching which is A1 to L of A1, then that matching cannot remain popular because that will leave P1 unmatched, right. So, it is a good thing. Here it does not affect, as we will see, it will not affect the case that it is popular or not. In fact, we should do this exercise. So, let us write this matching A1 P1, A2 L of A2, A3 P2, A4 P5 and A5 L of A5, right. Sorry, no, not L of A5, A5 P3, right. This is one matching, and what I will say is, I will just not write A1 P1 remains matched the same way, A2 gets matched to P2, A3 gets matched to P4, A4 gets matched to P5 and A5 gets matched to P3. Let us see how do these matchings compare in terms of their popularity, right. So, A1, A4 and A5 do not vote because they anyway are getting the same partners. What about A2? So, I will call them M and N. What is vote of A2? N. So, A2 votes here, right. What about A3? M, right. So, now these votes have got compensated. This does not prove that any of them is popular. We will show that these are popular, but certainly one of them is not beating the other. But one more thing we should observe is, what is the true size of this matching M? I mean, how many edges are there truly in this matching M? 4, because A2 L of A2 is really a dummy edge. We are just doing it for the sake of our convenience. That is not a true edge. So, whenever you match an applicant to its L of L post or last resort post, that is a dummy edge that you have matched, or that is a dummy match, and therefore you should not treat it as a true match. But what we will show is both these matchings are popular, and therefore it shows that in fact popular matchings come in different sizes. They can be of different size, and they indeed they can be different sized matchings. This matching is truly of size 5, this matching is of size 4 only, right. So, this is what this example illustrates. Is this fine? Yeah. Yeah, so we will see that, so as I said, I have not given an algorithm. We will see that our algorithm it must match every F post. Therefore, as a consequence, it will try to have fewer people matched to their S posts. But leaving somebody unmatched versus having more number of people matched does not affect the popularity, is what, if you for now believe that these two matchings are popular, this illustrates. Okay. So, what we have just defined is F post and S post. We will write the theorem and maybe prove some things and then, okay. So, what we know is that if M is popular, then every F post P is matched to an A belonging to F of P. Now, we will make the second claim, that is, if M is popular, every applicant is matched to either its FA or SA. So, I hope this notation is clear. F of an applicant, F of A is its rank 1 post, S of A is its most preferred post, which is a non-F post, right. And whether a true S post is there or not, we do not care. it may be its dummy last resort post. So we want to show this, that is, if M is popular, every applicant is matched to either its FA or SA, right. So let's look at an applicant's preference list. Its FA is its true top choice. There may be several posts here. There is SA, then there is something here possibly. This SA could be its last resort. If I take any arbitrary post here P, what can I say about P? What is there a property about P that I can say? It must be an F post. Some other applicant must be treating it P as its rank 1 post, right? Otherwise, this post would have been my S post, applicant A's S post. Good. So now what we will try to argue is that, so if M is popular, okay, so if M is popular, M of A is not equal to P. What do I mean by P? A post which is strictly nested between its F post and S post. This cannot happen. This is what I want to show, right. So what this claim says is that every applicant is matched to either its FA or SA. So if it is matched to its FA or SA, I am done. So the only possibilities are it is between FA and SA, or it is strictly worse than SA, right. There can be things like, in our example, this P5 is strictly worse than S of A3. So we would like to show that a popular matching cannot match it to that. So yeah, so if M is popular, then M of A cannot be equal to P. First we will argue that it cannot be strictly nested between F of A and S of A. So again we will ask, what happens if it is nested between its F of A and S of A? We just want to play the game, right? We are now used to it. So please use that and come up with an argument where you say that if you have such a matching, I will show you a more popular matching. Yeah, you had some argument. I would like everybody to participate. So yeah, again I would like to draw the picture. A is matched to P in this claimed popular matching. We know that this is neither its F post nor its S post. So its F post is somewhere better, F of A, and there is something more which you know by now, which you should use to get 2 promotions. Yeah, you want to try? Yeah, the penultimate row. Yeah, yeah. So at least please let us know, is there one applicant that you can promote? You understand what is promotions? Okay, somebody else wants to help her. Yeah, there may be somebody who is matched here. You have to demote that person. So let's call it A prime, okay? So good. So we know that there is some other applicant which is A double prime who treats P as its rank 1 post, right? And that applicant is not matched to P because P is matched to A. Therefore, we can promote A to P A double prime to P, A to F of A, and demote the applicant A prime to be unmatched, right, in which case we get 2 promotions at the cost of 1 demotion, and therefore we have argued that it cannot lie in this between F of A and S of A. A very similar argument will let you do that it is not strictly less than S of A. I will leave that as a small exercise, it is a very similar proof. So, I think we will stop here, we will complete the argument and we will show the algorithm what it does, but it is almost immediate now that we will draw this, we will construct this reduced graph and compute a maximum matching in this graph and do some adjustments to make sure that all F posts are matched.